Dear listeners, hello and welcome to the presentation of the project Performance Recovery Strategy and Advanced Control for Efficient Fuel Cell Operation, Protect for short. In this presentation, we are going to see first what the project is about, define the problem. Next, we are going to see the common approach how this problem can be solved. Next, we are going to show the strategy of how we did it. Next, we are going to see the results, what was the outcome of everything before, and we're then going to conclude the presentation. First, let's begin with the project overview. The project objective is to extend the service life of automotive PEM fuel cell systems through innovative operation and control strategies. There are a few goals which should be fulfilled in the scope of this project. They are listed here: low damage, startup and shutdown, consideration and extension of service lifetime and recovery strategies, new control processes for highly dynamic fuel cell operation, and a development of a fuel cell control unit. The project partners involved in this project are AVL from Graz, Technische Universität Graz, the Department of Chemistry from Technische Universität München from Germany, and us here, the Institute of Mechanics and Mechatronics from the Technische Universität Wien from Vienna here. Let's now see the approach that we're going to use. Here we have listed again the goals from the project. We are going to follow on only these two goals. The other goals are going to be addressed by the project partners. So, the goal of our institute here is to develop new control processes for highly dynamic fuel cell operation and consideration of an extension of service lifetime with recovery strategies. Usually, first, we need a model, which is based on some first principles, assumptions, and expert knowledge. Next, we need to parameterize the model. To do that, we have to design an experiment, collect the data, and determine the value of the parameters. Next, we're going to design a controller which needs first the control goals, which for us were going to be power tracking, extension of service lifetime, restrictions, and we need a suitable control strategy. Not all strategies are suitable for all control goals. And at the end, we usually validate the designed controller. We compare it with reality and do some testings on the real system. Let's now see the actual strategy that we used for this project. The first step was to develop a model. The structure is as follows. It consists of the cathode channel, where the air flows, the anode channel, where the hydrogen flows, and the electrochemical and water transport submodule, which couples the two channels. The cathode is described by the masses of all the species inside of it, denoted here by blue, and the anode is described with all the species flowing inside of it, denoted here by red, and there is also this dynamical relative humidity state, denoted here by black. The inputs coming outside to the system are the inlet pressure in the anode, the inlet mass flow of air entering the cathode, the back pressure valve position at the end of the cathode, the purge valve position at the end of the anode, and the actuating current. Here we can see the vector of states, the vector of inputs. But there is also one other vector, the vector of outputs. These are the quantities that we actually want to control. These are the net system power, the system efficiency, and the membrane overpressure, the pressure difference between anode and cathode. When we collect all the differential equations which describe the dynamics of all these states here, we end up with a transient nonlinear state space model, as you can see here. Now the first step is done, the model has been developed. We end up with a nonlinear state space model describing the system. The next step is to parameterize the model. Very briefly, the parameter sensitivity is first investigated to determine which parameters are most important to design the experiment, and then the parameters are estimated via a network of local linear models. Remember, we had a non-linear model, so we linearize the model around several crucial operating points and use those linear models to estimate the parameters. Let's now define the control goal. The project goals are given here, and once we reformulate them, we can say the following. The control goal is to deliver the requested power demand as fast and efficiently as possible while ensuring safe operation. Which further means we need to do power reference tracking, efficiency maximization, and we need to respect all the safety constraints. This is the goal that we have to fulfill with our controller for fuel cell systems. The control strategy that we used is called Model Predictive Control, MPC for short. We use the model to predict the future outputs and then use that information to optimize the inputs that have to enter the system to achieve the desired outputs. As stated, the MPC is an optimization problem, which consists of the output error cost, the difference between the predicted and reference outputs, and the control move cost, which tells us how much effort we put into the controller. We don't want this to be too big, which would in turn mean that the controller behaves very aggressively. This cost function should be minimized, meaning that the outputs, the predicted outputs, should match the desired outputs, and the control move should be low, meaning that the controller is not very aggressive. The MPC performance is defined by the horizons, the prediction and control horizon, in weighting matrices, which determine the aggressiveness or sluggishness and the size of the optimization problem. Longer horizons means better predictions, but higher computational cost. This is a strategy that we used. We want to minimize this cost function to get the optimal solution. Global optimum and efficient solution search are guaranteed for the linear systems only. And remember, we have a non-linear model at hand. So what we do here is we successively linearize the model. So at each time step in our simulation, we calculated the linear system which represents the nonlinear model correctly at that point or in the vicinity of that point. And if we do that successively, we have a series of linear systems which represent the model correctly at every point in time. After we have the model, we do the prediction, as you saw in the cost function. We do the prediction using that model, then the global optimum is found and the system matrix is updated and the procedure is repeated again. Then we are sure to have a global optimum at each point in time, ensuring an optimal solution. Let's see now some results from this research. On the bottom left, you can see the vehicle from which the data has been acquired. In this plot, you can see that the measured power demand was successfully delivered using our successively linearized model predictive controller. You can see that our controller in the simulation environment behaves similarly to the vehicle itself. So the power demand has been successfully delivered. The next goals were efficiency and safety. For efficient operation, you can see on the top left plot that compressor power has been reduced. So if our control strategy would be employed, less compressor power would be used. On the top right plot, you can see that system efficiency overall will be higher. That's the blue line. In turn, it means that the fuel cell operates at higher voltages, as you can see from the bottom left plot, which in turn means, as you can see on the right bottom plot, that the current is usually lower, which means that less hydrogen is consumed, so fuel is saved. Safety is the next goal. Model predictive control can handle constraints. If we set a constraint of the stoichiometry of oxygen, as you can see from the top plot, to 1, the MPC will respect it. And operating at lower stoichiometries is favorable for efficiency because we have less oxygen, meaning we need less compressor power. But again, we have enough oxygen for the reaction to be completed safely. On the bottom plot, you can see the hydrogen stoichiometry with some interesting spikes. The spikes correspond to purging events. So during purging, the hydrogen leaves the system abruptly. And these spikes are the reaction to a purging event. So hydrogen is replenished so that the pressure doesn't drop below safe levels. Another very important aspect of safety is compressor operation. As you can see from the right plot and the red and blue lines, which represent the vehicle and our controller respectively, operate along this reference line, which is in the middle of the compressor map. The surge line and the choke line denote the lines at which mechanical failure happens. A simulation test was performed where this reference line was not taken into account. And then the controller, all it wanted to do was to reduce compressor power. And those are the green lines. It means that it wants to operate close to the choke line because the compressor power is lowest there. However, that's unsafe. That's why it's important to include this reference line into the controller. The highlight here is that this reference line is very easy to implement. Any additional safety constraint or safety requirement or efficiency requirement that you might come up with can easily be incorporated into the controller. And then it will optimally choose the solution which satisfies the power demand tracking, the efficiency operation, and the safety requirements. That is the strength of model predictive control. It can handle constraints and it can solve the system optimally. The goals that we wanted to fulfill are listed here. Again, the new control processes for highly dynamic fuel cell operation is actually our successively linearization MPC. And the consideration and extension of service lifetime with recovery strategies is our predictive capability of the MPC plus all the constraints that we have imposed. With this, the goals have been fulfilled. We managed to deliver the power demand while exercising efficiency and safety. Thank you for your attention, and if you found this presentation interesting, please do not hesitate to contact us here at our Institute of Mechanics and Mechatronics from the TU Vienna.